Hey there, welcome to week 3. This is going to be chapter 2, part 1. Okay, so week 3 and chapter 2, part 1. So in chapter 2, we begin with a variety of things. One of the things we begin with is a little bit of a history of chemistry, and it's a very small portion of history, but it talks about a variety of different laws. And I'm not going to go over all of those here because there's a lot of that in the slides in the annotations file that you can read. But what I want to do is I want to talk about a few of them that are very important. The first one is the law of conservation of mass. Well, what is the law of conservation of mass? In this case, to conserve means to keep. All right, so what we're really talking about here is that mass is kept, okay? And what we're actually saying is that we cannot create mass and we cannot destroy mass or matter for them, and matter always has mass. So the law of conservation of mass by Lavoisier is saying that matter cannot be created or destroyed. It can change its form, it can change where it is, it can change what state it's in, but we cannot actually completely destroy the mass and the matter of an object. And so even if, like, say there's an explosion and then, hey, you've got nothing here, that went somewhere. It didn't destroy what was there to the point where the molecules are just gone. Like, that doesn't exist. Okay, and that's the law of conservation of mass. And one of the ways that we're going to be using that, mainly when we get into chapter 3, is the idea that what you start with, you have to end with. Okay, so let's take a look throughout the next few slides. I'm going to be using an example called calcium chloride. Okay, and calcium chloride is an ionic compound, and you'll learn this next week. And it's one calcium with 2 chlorines stuck to it, CaCl2. And again, you're going to learn how to determine that next week. Don't worry too much about that right now. Okay, so in the law of conservation of mass, let's say that we have calcium solid plus chlorine gas. Now, chlorine is a diatomic, which means it always exists paired in nature. And when we combine those, we end up with CaCl2, okay? And calcium chloride is a solid, it's an ice melt. So here we have our equation. And again, you're going to see these in chapter 3. Don't worry about them too much right now. But what we're looking at here is that if we have 1 calcium on this side and 2 chlorines on this side, then we will end up with 1 calcium on this side and 2 chlorines on this side. So you'll have 1 calcium and 2 chlorines in the reactants and 1 calcium and 2 chlorines in the products. Law of conservation of mass says, though, that basically, let's say that we start with 10 calciums and 20 chlorines. That means that in the end, we will still have 10 calciums and 20 chlorines. So no matter what we have going on here, this is never going, you will always have the same number on this side that you have on this side, okay? And so that's really what we're looking at with the law of conservation of mass, is that what you start with, so is that the reactants basically have to equal, the products. All right. Now the next one that we're going to talk about in here is definite proportions. And you can read about what definite proportions are, but let's take a look at definite proportions in terms of where it really becomes important. And definite proportions is basically saying that one compound contains the same ratio of elements by mass, no matter what size of a sample that you have. Okay, so let's look at our calcium chloride again, CaCl2. Now, I'm going to be putting some numbers on the board. You don't have to worry yet where those numbers are coming from, because we'll be learning how to take molar masses in the next chapter, in chapter 2. So right now, I'm just going to give you some idea. Calcium chloride is 36.113% calcium by mass, and it is 63.887% chlorine by mass. Okay, so that means that no matter what we have, we will always have this percentage, this ratio. Okay, so let's take a little bit of a step here away from this, and we'll come back to it. But first, let's talk about some math. A proportion is two ratios that are stuck together. Okay, so for example, let's say that we want to make a sandwich, and our sandwich would have 2 slices of bread and one slice of cheese and 3 slices of ham. I'm just making this up. We'll say 3 slices of meat, whatever kind of meat you like to put on your sandwiches. If you're a vegetarian, submit something else. This is just for, illustrative purposes. Okay, so what this means is that our ratio of bread to cheese, for example, is maybe 2 to 1. Our ratio out of this example of bread to meat would be 2 to 3. Okay. Now, let's say that this is one total sandwich. Let's say that we want to make 5 sandwiches. Okay, well, we can then use this idea, this information, of course, to say, well, then in 5 sandwiches, I will have 10 slices of bread and 5 slices of cheese, or 10 slices of bread and 15 pieces of meat. So this is proportions math, ratios math that you would do in your head, and we're going to do it the same way here. Sorry about this. It's going to take a while, but I want to keep the rest of it there. There we go. Okay. So now let's imagine what this means. Okay. If our sample size for our calcium chloride is 100 grams, and I'm going to give it all kinds of sig figs there. Here, I'll make it neat too. Then that means that I have 5 significant figures here. Then that means that I have 36.113 grams of calcium and 63.887 grams of chlorine. If my sample size is 1 gram, then my proportions here, are going to, I can set it up, because this is what percent means. Remember, percent means part out of 100. And that's going to end up being really important too in chapter 3 when we're doing percent compositions. Okay, but here we have 36.113% carbon. And so that means part out of 100. So if our sample size is 100, this is our mass. Well, we could set up a proportion to solve this. I know some of you are already ahead of me in the math, and that's okay. Okay, well, what this says is that then if we have 36.113 grams of calcium per 100 grams, okay, so this is calcium to total. And I know I'm going through this slowly, but this is just so that we can review the idea of proportions and ratios. Okay, well, now I want to know, okay, I have 1 gram and I want to know X. What's the mass on my calcium? And I'm showing this all out so that you can see this is how you solve this kind of a proportion. It's called cross multiplication. And you're going to multiply what's here and divide by what's left over. And that means that then our X will equal 36.113 times 1. And I'm cutting off my significant figures here, so, but I know that they're there originally, divided by 100. So the mass of my calcium is going to be 0.36113. I could do this proportion for anything as long as I have that percent. So let's say then that my sample size, I'll go ahead and do another one. Let's say that I have a sample size of 26 grams. And I want to know how much calcium I have. Well, let's switch. Let's do it with chlorine now. Okay. Now I have a sample size of 26 grams. Okay. Well, now it's not so easy to do in our head. Okay. So we're going to set it up still. And here I want to know what the mass of my chlorine is. So I set up my proportion. I had that 63.887. So I say, okay, well, I know that I have 63.887 grams of chlorine. And I'm going to go ahead and take all my units out. Over 100. Yes, there are other ways of doing this. Okay, and we're just doing this to review proportions. If you can see this and you're like, oh, I already know how to do the math for that, and I do it in a different way, absolutely fine. I don't care what method you use, as long as it's your method and not copied off the internet. Okay, if you don't already have a method, try mine. All right, so now we have 100 grams total is that original sample size, and now we have 26 grams. Okay, oh, and I said I wanted to leave off the units for the moment. Okay, and here I'll have my X. And remember, X is my mass of chlorine. So now I'll solve for chlorine, and I won't rewrite it in its entirety, but I will go ahead and show. Here I have that cross multiplication, and just like over here, it's going to be 63.887 times 26 divided by 100. Okay, and I'll end up with my chlorine equal to 16. Now I can only have 3 significant figures. So this becomes 16.6 grams. Okay, so that's one way to do the math for this type of problem. And like I said, I chose this way just so that we could review the idea of proportions and ratios, because it's going to come in really, really handy when we do stoichiometry next semester. If you're already really comfortable with the idea of percentages and parts out of a whole, and you can do this using percentage math, please feel free to do that. That's fine. Okay, so now let's take a look at the next topic that we want to look at. Okay, and that is often known as Avogadro's hypothesis. And I think what's very confusing hypothesis in this textbook is that in chapter 2, they refer to it as Avogadro's hypothesis, okay? And then in chapter 5 as Avogadro's law. And it's the same thing. So you'll see this in different ways. If I refer to it as Avogadro's law instead of Avogadro's hypothesis, just know that they mean the same thing. And what it's really talking about is that compounds will have the gaseous compounds. Let me back up a minute. Gaseous compounds will occupy space based on how many there are, not based on their mass. Okay, so let's take a look a little bit from, and this is from the slides, but let's take a look at what that means. Okay, let's say that we have one hydrogen molecule. And a hydrogen molecule is a couple of little tiny hydrogens stuck together. Okay, and now we're going to need 2 of these little hydrogen molecules because we're going to make water. Try to make them about the same size. Okay, so here we have 2 little hydrogen molecules. And this is our standard volume. That's all we're going to say about that. This is our standard volume. Okay, and this little hydrogen molecule is about 2 grams, and this one is about 2 grams. Now we have one great big oxygen molecule. Now oxygen is a lot bigger. Okay, than our hydrogen. This is an O2 molecule. So I'm calling it a molecule. It's a diatomic gas. Okay, so it's in its elemental form, but they're stuck together like a molecule. Okay, and this one is 32 grams. And again, you don't have to worry too much about that yet. That will come. All right, well, what happens with this? We know that 1 oxygen and 2 hydrogens forms water, H2O. You all are accustomed to that. Okay, but we have 2 oxygens and 2 oxygen atoms and 2 sets of 2 hydrogens, which means that we can make 2 water molecules. And each one will have an oxygen and 2 little hydrogens on it. And so we can see that in this one, now what we have is we have an H2O and an H2O. And this one is 18 grams, and this one is 18 grams. Now, remember that law of conservation of mass, right? Well, here I have 36 grams, and here I have 36 grams. Okay. Now, what we find here is that we have 1, 2, 3 molecules of gas on our reactant side and 1, 2 molecules of gas on our product side. We have 3 molecules making 2 molecules. But the masses don't change. We have 36 grams equals 36 grams. Then we have 3 molecules make 2 molecules. Okay, and so we've gone from 3 to 2. Well, what that means is that this is taking up 3 units of volume and this is taking up 2 units of volume. And that's another ratio that we're going to be using. So in this case, what we have here is that we have 3 molecules becoming 2 molecules. And we can count them, 1, 2, 3. So we have 3 units of volume. 1, 2, making 2 units of volume. And so what that means is that Avogadro's law or Avogadro's hypothesis is saying that the volume of a gas is proportional to the number of molecules or the number of particles that you have. So if you had something like neon or argon that's not diatomic, then you'd be looking at single gas particles. So the number of particles is linked to the volume. And that's what Avogadro's law is saying. Okay. All right. The next thing that we're looking at is Dalton's atomic theory. I'm not going to go through all the parts of Dalton's atomic theory. You guys can read this and you can watch the videos and you can and read the annotations on your own. The one thing that I want to point out for Dalton's atomic theory is that out of all the things that we now know are true, there's one big one that's not. And one of the things that Dalton's atomic theory said was that all atoms of a given element are identical. And we know now that they are not. And the reason that they are not is because of something called isotopes. Okay. And excuse me, isotopes have different numbers of neutrons in them. So let's come back to isotopes for a minute. Let's talk about atoms in general. So let's talk about the atom. In the center of our atom is the nucleus. The nucleus is extremely dense, and it contains almost all of the mass for the entire atom. If the nucleus was the size of a marble, the electron cloud, the atom itself, would be the size of a football field. But all of the mass in it would be in the marble, and there would be no mass in the rest of the football field. Okay? The nucleus is composed of two different things. It's composed of protons, and these are positively charged. Sometimes I'll refer to them as P+. Okay, they're positively charged, and neutrons. And sometimes I'll refer to those as N0. And neutrons are neutral. They don't have a charge. They do, however, have mass. And the proton has a mass of about 1.673 times 10 to the negative 27th kilograms. And the neutron is pretty much the same. It's 1.675 times 10 to the negative 27th kilograms. Okay, so these are all stuck together in the nucleus. Okay, sorry, these are all stuck together in the nucleus, and that's where all the mass is. Now, outside in the cloud, we have electrons. Okay, and electrons make up this huge cloud compared to our very dense nucleus because they are moving constantly and very, 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 very fast. Okay, and sometimes we'll abbreviate electrons as an E-, and they are so small, it's 9.109 times 10 to the negative 31 kilograms. Now, these orders of magnitude are outside of the range of what we're accustomed to. Let's see this 27 to negative 31. The protons and the neutrons are each more than 1,000 times bigger than the electron. Okay, so it doesn't look like a big deal here. It's only a few difference, but it's huge because it's an order of magnitude in scientific notation. So protons and neutrons are more than 1,000 times bigger than electrons, which is why pretty much all the mass is right there in the center of our atom. Okay, well, let's come back to neutrons. Neutrons don't actually change anything. They just add mass. And most elements are a mixture of isotopes in them. So what's an isotope? Well, an isotope is something that has the same number of protons and electrons, because the protons and electrons are what determine what atom we have, okay? But they have different numbers of neutrons. So an example of that, I've lost where I am in my slides. Don't worry about it. Okay, an example of that is carbon. Carbon is made up of carbon 12 and carbon 13 and carbon 14. And again, in chapter 3, we'll be working more about this. You'll be learning exactly where the mass numbers on the periodic table come from, why they aren't even. But right now, we're just going to focus on some ideas. So carbon has, and actually, let me go ahead and let's go look at the periodic table for a minute. Okay, I have a couple here. This one is kind of blown up a little bit. I'm gonna move things around on my screen just a little bit. Okay, so now let's take a look at this. We're talking now about carbon. Okay, and carbon on your periodic table is right here. Oh, that's kind of hard to see. Let's see if I can get that to be a little bit wider. All right, there we go. Here's carbon on our periodic table. Okay, and what does this mean? All right, I'm just going to, I have to move things around so that I can kind of get my space. And you guys can't see what I'm doing, so don't worry too much about it. Okay, so here we have this symbol here. You see, first of all, we'll start here. That's not what I want to do, but it's okay. All right. See, there we have our name. And it's carbon. Okay, now we can see this C right here, and that's our symbol. And in that case, it's a C. All right, now let's look at a couple of other things. You see this 6 right here? This 6 is our atomic number. Number sign, not hashtag. The atomic number is 6. Well, what does that mean? That is the same thing as the number of protons. So that means that we have 6 protons. Now, when we are neutral, we also have 6 electrons. Okay, so in a neutral atom, that's 6 electrons. And now, last but not least, down here, you can see that we have a mass number. And the mass number is equal to the protons plus the neutrons. Okay. Protons plus neutrons. Well, it's 12.011, so it's not exactly 12. Let's take a look at that. Okay, I'm going to stop the share, and then we'll go back to the whiteboard. Okay, so what we had there, and I apologize, just moving things around on the screen. Again, you guys can't see that, but there's all kinds of things on my screen that's in the way. Okay, so we have carbon 12. Carbon 12 means that we have a mass number of 12. Mass number. But all carbon has the exact same number of protons. So carbon 12 has 6 protons, and carbon 13, which I'll get to in a minute, has 6 protons, and carbon 14 has 6 protons. That doesn't change. Okay, what does change, you'll see, is this mass number. So what does that mean? Well, remember we said that the mass number was equal to the protons plus the neutrons. So if we have 6 protons and our mass number is 12, that means that we have 6 neutrons. If our mass number is 13 and we have 6 protons, and that means that we have 7 neutrons. If our mass number is 14 and we have 6 protons, that means we have 8 neutrons. Now, all of these are neutral. These are all neutral. How do I know that? There's no charge. If I have said specifically that there's no charge, then I know that that means that my protons and my electrons are the same. So if I have no charge, then I have 6 positive charges and I have 6 negative charges. Okay, so this is an isotope. This is a neutral isotope. It is not an ion. We'll get to that in a bit. This is a neutral isotope. And this is what makes atoms within an element different from each other. Okay, so let's take a look at another example. Okay, and what we're going to do now is we're going to look at manganese 55. Okay. Now notice there's no charge, and so because there's no charge, this is neutral. Now what I'm going to do is I'm going to go find manganese on my periodic table, and you should have a printed periodic table as well. That was one of the things that I mentioned. If you do not have a printed periodic table, you need to email me right away if you cannot get a printed periodic table for me to send it to you. I very much do not want you using periodic table either on a second device or on a second screen or in another screen on a test. And there's 2 reasons for that. Number one, I don't want you on your computer or your phone during a test. But second, what I have found is that when students break that rule and try to use it on another device, they don't do a very good job. I actually have had students say, oh yeah, I broke that rule for that test, but I'm really glad I have a paper one for this test. So if you cannot, absolutely cannot print it, please contact me and I will mail you one so that you have it. So let's look for manganese. Manganese I would find on my periodic table, and it is number 25. And this is what it looks like on your periodic table. It's got the word manganese up at the top in very little writing. And then it has a 25 here. And then it has an MN here. And then it has 54.938 listed here. Okay. Now this mass number is not a single mass number. It's a weighted average of all possible isotopes. Okay. So sometimes it'll match, but sometimes it will not. Okay. Kind of like how with carbon 14 has a mass number of 14, which isn't anywhere near 12. Okay. But let's take a look at this. And what we're going to do is we're going to learn how to make a symbol. And this special symbol looks like this, X with an A and a Z. And what are these? Okay, well, this X is the atomic symbol. And the A here is the mass number, which sounds really weird because you think it should be atomic number, but it's not. It's mass number, which remember is protons plus neutrons. And the Z is the atomic number. And the atomic number, remember, is our number of protons. So if I was going to fill in, if I was going to create this symbol for manganese, I would say, okay, well, first of all, I have manganese 55 right here. So I know that that means that my mass number that I'm going to put here is 55. If this was, say, manganese 53, I would put a 53 here. All right, and then I have my symbol Mn right here. And then I need my atomic number, which is right here, and I put that there. So this is a symbol that tells me exactly which isotope of manganese I'm working with. Okay, and you guys are going to be doing more of that as time goes on. All right, so now though, let's take a look at the concept of ions. So isotopes have different numbers of neutrons. But the same numbers of protons, same numbers of electrons, because isotopes are often referring to neutral elements or neutral atoms. Sometimes, however, what we'll end up with is we end up with something called ions. Now in ions, we have either lost or gained electrons. Okay, so let's take a look at a couple different things. Let's look specifically at Li+. All right, now lithium with a 1 plus charge. So yeah, there's just 1 plus charge there. And then let's also look at magnesium. And that's going to have a 2 plus charge. And we'll talk about in a bit about how you can predict those. And then as we're going across, let's look at oxygen with a 2 minus charge and fluorine with a 1 minus charge. Now, I know that these are not neutral because of these pluses and minuses. Okay, and the 1 is understood, but I'll go ahead and put a 1 there. And what this means is that here we have lost 1 electron. The magnesium has lost 2 electrons. This oxygen has gained 2 electrons. And this fluorine has gained, whoops. And this fluorine has gained 1 electron. And that's what that means. So that means that the number of electrons is going to be different now than the number of protons. Okay, so let's take a look at our periodic table. And again, I'm not always going to toggle back and forth. So make sure during these lectures that you have your printed periodic table next to you. Okay, so first of all, here we have lithium, and I look at lithium on here and I see that it is number 3. So because of that, I know that it has 3 protons. Okay, now let's say then that we've lost 1 electron here. So that means that we have 2 electrons. All right, and let's say that this comes from lithium 7. Okay, so if this is lithium 7, okay, then that means that we have 4 neutrons. And we could create a symbol that looks like this, Li, 1 plus, and a 7, and a 3. Now let's look at our magnesium. And we're going to say that this is, and actually hang on just a second. I like to keep things kind of clear. So we said that this was lithium 7. I'm going to say that this one is magnesium 24. Okay, so now what we have is we have magnesium is number 12. That means that we have 12 protons, but we've lost 2 electrons, which means that we have 10 electrons. If we're working with magnesium 24 specifically, then that means that we have 12 neutrons, because neutrons plus protons equals mass number. And so now the symbol, and you'll see that we have charges on these, and we didn't have them on our previous slide. Now our symbol is 24 and 12 and Mg and a 2 plus. Now let's look at our oxygen here. Okay, and let's say specifically, actually, let's do one that's a little different. We're going to say that this is oxygen 18. So that means, well, oxygen is number 8, so we have 8 protons. And we have gained 2 electrons. That's what that -2 means. Gained 2 electrons, which means now that we have 10 electrons. So you'll see here we lost them, and our electrons were less than our protons. Here we're gaining them, so our electrons are more than our protons. And our protons plus our neutrons equal our mass number for 18, which means that in this case we have 10 neutrons. Okay, so our symbol here would be 18. And 8 for our protons, and O, and a 2 minus charge on it. Now let's look at fluorine, okay? And for this, we're gonna say that we're working with fluorine 19, okay? And if I look at my periodic table, I see fluorine is number 9. Definitely be doing this. You have to be very familiar with where your things are on your periodic table. 9 protons, because it's number 9. And we've gained 1 electron, so now we have 10 electrons. So O2 minus and F1 minus have the same number of electrons, but different numbers of protons. And fluorine 19, so 9 plus 10, okay, so this is 10 neutrons for this one, is for this isotope and ion as well. And so then we'll come down here and we'll say, oh, we have 19, an F, and 9, and a 1 minus charge. And that's the symbol for this. Okay, that covers most of what you're going to be working with. I want to look one last time at the periodic table. And and I want to look at this a little bit. Okay, let me again move things around on my screen just a little bit. I think that should be good enough. Okay, so let's take a look at this a bit now. I'm gonna have to move this around multiple times. There we go. Maybe not. Okay. So let's look at some things, because one thing that's really important now is that we need to be able to identify where things are on our periodic table. So first of all, you see everything here that I'm coloring in blue. Actually, hang on. Okay, everything here that I'm covering, I want to look at this in a different way. Everything here that I have in blue, okay, these are what we call group 1. Okay, so there's our group number here, group 1. And these hydrogen as well is group 1, and these form 1+ charges, which means they lose 1 electron. Hydrogen is its own thing, but everything that I have here marked in blue, not hydrogen, that's a big thing, because hydrogen is a gas, not a metal. Everything that I have marked here in blue is an alkali metal. Okay, now let's look at the one right next to it. Ooh. There we go. Let's look at this column now. And I kind of recommend, if you have crayons at home or colored pencils, that you go ahead and color in your periodic table to match. It's going to make things a lot easier down the road. Okay, this is group 2, and these tend to form 2+ ions, and they are called alkaline earth metals. All right, now let's come over to the side for a moment, and I'm going to color all these in nice and bright yellow. These are group 8, and I'm going to put an 8 here. They have an 18 written. This is group 8. You're going to hear it referred to as group 8 way more than you're going to hear it referred to as group 18. And these are our noble gases. And our noble gases do not form charges. Sometimes you can get the bigger ones to form molecules, but they're rare, and they do not form ions. They do not gain or lose electrons ever. All right, so now let's look at our next one right here. And we have group 7. And group 7 are our halogens. Halogens always lose 1 electron and form a 1- charge. Now we're starting to get a little bit outside of where we have like rules about everything. Here we have group 6. Oops, sorry. Here we have group 6. These tend to form 2- charges. And notice that I didn't go all the way down here because things get weird. Okay, things get weird down here as well, but we won't worry too much about it. These form 2- charges, and they don't have a special group name. They're just group 6. Okay, and then here we'll have these tend to form, these don't have a special group name either, they're just group 5, and these tend to form 3- charges. And then as we come back over to, let's see, here, these tend to form, and notice I'm not going too far down because once we go farther down, this is group 3, okay, and they tend to form 3+ charges sometimes, but they're not always. It's kind of weird. All right, and then here we have things that don't usually form ions. Okay, all right, so that just sort of gives you a little bit of a crash course in what we're working on here. One of the things in the slides is a slide that shows metals versus non-metals, and that will be helpful as well. I look forward to seeing you in recitation. Bye.